All right. Good morning, Organic Chemistry 2341, section 253, which is at 8 o'clock in the morning on this very cold Thursday morning. It was 33 degrees out at my house. And so I hope you are staying bundled up and nice and warm. Anyway, so I wanted to give you a heads up that if you go to Canvas and look at the lecture and exam schedule, you'll see that I will even share my screen. Lecture and exam schedule. Right here, if you look at the screen right here, we have, we're going to finish up module 4 today. And then I actually have an extra lecture on resonant structures that I'll get to today. I keep it unless I have time for it. And then on next Tuesday, we're going to have a review. Now, to help you with the review, there are a set of slides on Canvas called Hot Topics Chapters 1 through 4. Okay, go to Canvas under, if you go to your home page and you hit your resources button, it's under the resources here. And so exam review hot topics. So that's going to have the top topics that we'll be having on this exam. And so I wanted to make sure you saw that that's there and start with that, start studying that, review the homework. The homework's available for you for review. So you can try it again and see if you're getting it right. You know, look at the topic, do a homework problem. Did you get it right again? Yes, that's great. If you didn't, go ahead and read and maybe focus on working on that one. Okay. The exam will be held on Top Hat. So you must have Top Hat to be able to take the exam. We're going to do it on Proctorio. On Proctorio, actually, let me stop sharing. So on Proctorio, what they're going to ask you to do is that you're going to have your ID, you're going to have your computer. I'll send out instructions the day before about it's best to have your computer rebooted and have nothing else open. Okay, that's the way Proctorio really likes to have it. It's going to ask for your ID. You're going to log into Top Hat. You're going to show your room, and then you're going to begin your exam. Okay. I am going to be live monitoring my email during the exam. So if you have issues, go ahead and just email me. And sometimes people get kicked out because a dog barks or something like that. But Proctorio is a lot less sensitive than the examity issues that we were having. And it's 100%, it's just a video recording of your test taking. So there's nobody looking at you while you're testing. Don't even worry about that. Just go ahead and focus on the problems. Now, if there's some anomaly and the artificial intelligence filter says that, oh, there was a lot of there's a lot of things happening in the background, so there's a suspicion, then I'll review it and look at and see that your cat just jumped on your keyboard for that scene. So usually it's something simple like that. And the good thing is I have those videos for review. So and so I really actually never look at them unless there's a high level of suspicion picked up by the AI. So just imagine, you know, that you are taking an exam in a nice quiet room and nobody's staring at you. So it'll be less stressful than some. You will be able to have a couple pages of scratch paper and you're going to show them to the camera before and after so that you're not writing down all the answers or anything like that. So, and that'll be in the instructions as well. Have a Chromebook. I believe that the Chromebook does, we have a Chromebook. I think Top Hat does work on a Chromebook. I would go to Top Hat information and see. I'm pretty sure it does because it worked on my iPad the first few times, but they changed the instructor version of the app, so it doesn't work on my iPad now. But I would double check that. I think it does. Okay. And so I really like the Top Hat exam format. It's going to be 30 questions, multiple choice. You'll have an hour and 20 minutes to take it. If you have ODS accommodations, you'll have longer. And so I'll be sending out emails about whether you want to start early or stay late, depending on your class schedule. And again, I'll have those instructions sent out the day before, so you have plenty of time to look them over and be able to do that. So again, our exam is on Thursday of next week. And I'm pulling up the date. I think it's the 17th. Don't write that number down yet.
I think it's the 18th.
It's the 18th, yeah. It says it's on the 18th. There's a typo in the exam schedule saying it's on the 17th, but it is on the 18th. Okay, so next Thursday during regular class time, don't come to Zoom, go straight to Top Hat and start taking your exam. Okay, questions on the exam and the review materials that are already available to you. Okay, let me go ahead and share my screen and let's continue on with chapter 4. Okay, let's see. Share screen. Okay, so I'm going to move this once because it doesn't like when I move it. All right, can we see my shared screen with the slides on it? Okay. Regular ID will work, either one. It has to have a picture and your name on it. Okay, and so you just have to have a student ID or a regular ID. Occasionally, it'll flag it, and it will I'll have to just look at it and say, yeah, that is your ID. There will be a periodic table on the exam at the beginning and the end of the exam. You have to know the trend of electroactivity yourself, but there will be a periodic table on all the exams. There's one at the beginning of the exam and the one at the end of the exam, so you can go to whichever one's closer. Okay. Any other questions on the exam? Those are great questions, by the way.
Will we do any review in class or no?
Yes, we're going to do a review in class next Tuesday.
Okay, great.
Okay. And that's on the exam and lecture schedule as well, which is found on Canvas. I'm beginning to like Canvas now that I figured out how to put those buttons in there. It makes things so much easier. Okay, so last time we were talking about the chair and configuration on cyclohexane and why it's the most stable, why it has 0 ring strain, because you can arrange it so every bond has that 109-degree angle and none of the atoms are eclipsed. They are all in their staggered or gauche configurations. So that's why we have that as the most stable configuration for this. And then we ended with figuring out how to draw the structure. And I'm going to go over that one more time right here. So the first thing we want to do is we want to draw our 2 parallel lines going this direction. Then we can draw 2 parallel lines going that direction, and then 2 parallel lines going that direction, and that gives us our system. And then the next thing we do is we put all of our axials. Remember, our axials are the ones that are going up and down along with the axis. If this was a planet, this would be spinning on its axis, and we have the ones aligned with that axis are our axials, and the ones that go around the equator are our equatorials. And then we can add all our hydrogens out here somewhere. Obviously, it's hard to draw them all in place, but we can. So knowing that and that chair configuration, let's talk a little bit more about cyclohexanes. Okay. So the next thing we want to talk about is that when we go from a chair position and it goes through that boat configuration into the other chair position, what happens is that the axial hydrogens, or the actual attachments, whatever they are, will become equatorial when you do the flip. And the equatorials will become the axials when you do the flip. Okay, so that's a very important thing here, because if there's only an energy barrier and you're heating this solution, it can go flip back and forth until it finds the most stable conformation possible. Okay, if they're all hydrogens, these two configurations have exactly the same equal energy. But let's say we put some big group here. Now our energy has changed. So knowing that when we flip these back and forth under this, I'm going from the axial position to the equatorial position, we need to find where to put this big group so it's most stable. Okay. All right, so let's look at just putting one methyl group on there. Okay, so in the case of this, we've taken one of those hydrogens off, put one methyl group on there, and by name it's methyl cyclohexane. And you could put one methyl cyclohexane if you wanted to. So if we redraw it such that we show it in this weird configuration here, this shows us that we have 6 hydrogens on the bottom, 5 hydrogens and a methyl group on top. So let's convert that to our chair configuration. And when we do that, we can draw something like this. And since this is pointing up, we're going to put it up to start with. And we're going to have it in our axial position. And notice that, again, all the red hydrogens here, or all the red substituents here, are in their axial position at this time, okay? So those are all axial, okay? But we're going to watch where that methyl group goes. Now, when we do our ring flip, that axial methyl group now becomes an equatorial methyl group, okay? So it's way out here on where's, oh, that's why. It's way out here on the end. It becomes that equatorial group, okay? So there has to be a reason why this equilibrium is shifted in this direction, okay? And if we look at it, this methyl group actually has 3 hydrogens on it, right? And if we draw the hydrogens here, this group is, this hydrogen is starting to come in close association with these 2 hydrogens here, okay? So remember, the axial hydrogens are closer together than the equatorial hydrogens, but they all kind of balance out. Now with this big methyl group, imagine it's taking up a lot more space electronically, and it's starting to be repelled by the electrons of the clouds of the 2 hydrogens, okay? So there is a barrier to doing this, okay? Now, when we have it way out here at the axial here, these hydrogens are now much further away from this methyl group, and therefore it's more stable. All right, let's take another kind of, this is a weird drawing. This is called a different kind of line drawing, but it has the hydrogens are the little white things at the ends here. These are all hydrogens, and the blue parts are the methyl groups. And so they're showing you that this hydrogen is really close to it compared with the hydrogens that are on the bottom of the axial. They're really far apart. So that proximity of that hydrogen to those other 2 hydrogens has an energy barrier to it. It wants to be repelled. It creates a little strain. Therefore, where the methyl group shows up here, I really want to get rid of that. Where the methyl group shows up here, come on. See how much further away these 2 hydrogens are? This is its closest equatorial hydrogen. This is its closest equatorial hydrogen. That is much farther away than the 2 axial hydrogens we see here. That's why it's more stable, okay? And because it's more stable, it spends more of its time in that configuration. Is it always 100% that? Well, not with methyl group. It's not a big enough group to do that. But I bet we can find a big enough group that it's like that almost 100% of the time. Okay, so let's look at it from the perspective of a Newman diagram and see that proximity as well, okay? So if we look at that interaction we were talking about, this methyl group and the hydrogens associated with are very close to these hydrogens in this configuration. And if we take a look at that, we see that this methyl group is gauche to this methyl group going through this. If we're looking down this bond and we draw our Newman projection of that, we can see that they're gauche, okay? Now, let's draw our Newman projection where we have one of our bonds is this one, and the other part of our Newman projection is this one. Notice that they're the 2 in the parallel lines. And we draw that as a Newman projection here. We see that in that case, the methyl group on the rear carbon here is gauche to the methylene attachment on the front carbon. So they're 60 degrees apart, so they're not eclipsed, but they are in that gauche position. Okay, so that takes additional energy. Now, what if we flip that over and put that in the equatorial position right here? So now let's draw that same Newman projection, but we're going to do it with those same bonds, this 2,3 bond right here and this 5,6 bond over here. And we're going to draw that Newman projection right here. And now look what we have. This methyl group, now that it's down because it's flipped over, is now opposite the other methylene here. That puts it into an anti-configuration. Those 2 attachments are in an anti-configuration, meaning and that is the most stable configuration we can have for these types of systems. So by being able to convert from that chair position to the Newman projection, you can see that, yes, this one is going to be less stable because of that Gauss interaction. And this one's going to have, or not stable, let's say higher potential energy in this one than in this one because of this Gauss interaction. Okay, so do we see why that in this case, the methyl group would want to be in the equatorial position? Sorry, got somebody in the waiting room. Okay, there we go. Okay, so that being said, that's just one attachment. Okay, let's talk about things other than methyl groups. Okay, so as the thing gets bigger or has a bigger electronic cloud around it, like let's think chlorine, it has three lone pairs around it, right? That those electronic areas take up space. And so when we have something just like chlorine, it is is going to be in the equatorial position 83% of the time. Okay, you take a drop of Cyclohexane and you freeze it, and then you go look at all the isomers, and 83% of them will be in that equatorial position, and the other 17% will probably be in that axial position or somewhere in between, because it's always flipping back and forth. Okay, so if we look at the methyl group, which we saw that was about 95%. And methyl group's a little bit larger because those three other hydrogens spread out a bit and let it kind of start to impinge on those axial hydrogens. If we increase it to an ethyl group, well, it's still, about the same, only a little bit, 96%, because the hydrogens are still kind of small, and that methyl group can be rotated around. So it's not too much larger than a methyl group. And we see that 96%. By the time we put two methyl groups on there, we see it jump again because we only have one hydrogen, and so it's taking up even more space. And by the time we put three methyl groups on there, the classic T-butyl, where we have three methyl groups on there, this is a big, bulky substituent. We're going to see this big, bulky substituent time and time again, this T-butyl group here. And it's out there 99.9% of the time. Because once you try to put those three methyl groups with three hydrogens on it, look how big that gets right there. And so that's why it's going to be in that equatorial position 99% of the time. Questions on that? All right, so what if you have two things on there? Okay, well, now we have to think about, okay, where are they going to end up? You're going to want at least one of them on the equatorial position, or you'd prefer to have both of them on the equatorial position, if at all. So let's look at this particular conformer of the Dibromocyclohexane. Okay, so in this particular conformer right here, remember our wedges, our solid wedges coming out of the page at us, our dash wedge goes down below. So we need to convert that into one of our boat and chair, our chair configurations. And if we just do our first conversion where we saying, okay, we can either go by this direction where we put the bromine up and the bromine down, and then convert it to this other figure. What I like to do is I like to do it directly to the boat and chair configuration. And the way I would suggest doing it is we're going to draw our two parallel lines, and then our two parallel lines. And we're going to start with this one position. So we're going to have a bromine up, and we're going to have a bromine down, and we're going to have a hydrogen there and a hydrogen there. So all I've done is assigned the hydrogens and the bromines to the ring. Everything else is hydrogen, so I'm going to leave those off. When we do that, we ended up with this kind of configuration here. Okay. So this means this bromine is axial and this hydrogen is going to be equatorial. And let me draw the other one in blue here. And then this hydrogen right here and this bromine are on the other carbon for clarity here. And that this bromine is axial and this hydrogen is equatorial. Okay. So when we started out doing that, we have two large atoms with three lone pairs on them in that axial position. Okay. So let's try to flip the ring and see where they end up, right? So if we have a ring and all of our axial substituents become equatorial substituents, we just need to redraw our ring where our axial and equatorial, we have to draw it in the other direction though. So now we're going to redraw our ring where we have our parallel lines, parallel line, parallel line, and we're going to have our bromine here and our hydrogen here. Oh, I drew it wrong. Yeah, well, no, it's the same. And our bromine here and our hydrogen here. So our bromines that were axial, when they flip, become equatorial. Now we have both large groups equatorial. So that's going to be the reason this is shifted to that side. Our largest groups are both equatorial. Okay, so now let's take that and turn it into a Newman projection. And with our Newman projection, we're going to draw our axis down the 1,2 bond here and this 4,5 bond here. And when we do that, we want to pull that up right here. We see that our bromines are both axial right here. But the cool thing is, at least our bromines are both axial, but they're also anti to each other. Okay, so, but they do have the spatially close to these two hydrogens on each side. When we flip it over and draw that same Newman projection right here, we see that we have the bromines gauche to each other, but they're both on the equatorial position. Okay, so this is our 60 degrees, which is our gauche position. So if we didn't have these attachments here to the cyclohexane ring, this would be the more stable because we'd want the two biggest groups anti to each other. But because of the constraints of the ring, we want those two largest groups to be equatorial. And in that case, it does allow them to be in the gauche position. Questions on that? Okay, I'm going to pull it up again. So if we have two substituents on a ring, the more stable configuration is going to be with the two largest groups on an equatorial position. And in this case, we can actually put both of the groups on the equatorial position. What if we can't? Okay, so let's look at a different isomer here. Let's look at the 1,2 isomer. So in the case of the 1,2 cis isomer, the bromine's on the top and the bromine's on the top, okay? Which means when we draw this, we have to draw this like right here. And we're going to draw one bromine up right here, which puts the hydrogen at the equatorial position, and one bromine up, and because that hydrogen has to be below it there. So that means we have one bromine in an equatorial position and one in an axial position. Okay, so that's the easiest way to convert this drawing to this drawing here. Now, when we do that, we have the bromines are in a gauche configuration, but when we flip it, we end up with the exact same thing. There's going to be one bromine, the axial bromine. That's weird. The axial bromine will become an equatorial. That's the same picture. Okay, so that is weird. Okay, this equatorial bromine is going to become an axial bromine on the other one. Let me draw the other one here real quick. Okay, because that is not right. So when we flip it over, we're going to have a structure that looks like, let's see, we're going to have that. Oh, they've, there. It's sort of right. It's rotated a little bit. This is going to be our one carbon. No, our one carbon's up here, and this is our two carbon here. So they've rotated it around. That's what they did. Okay, so in our 1 carbon, our bromine now is in our axial position and our hydrogen is our equatorial position. But here on our number 2 carbon, that axial is now in the equatorial position and the hydrogen is now in that axial position. So no matter which way you flip it, you're going to go, so yeah, this is the same drawing. Yeah. So don't use that one, use this one down here. So here we have the bromine down, bromine in the equatorial position. This becomes equatorial and this becomes axial. So because we have one of the large groups at each of those positions, the equatorial and axial, and it doesn't matter which side we flip it, we have equal time that those 2 different isomers are going to exist, because we're going to have one equatorial, one axial, okay, if they're both the same size. So what if you have more? Okay, let's talk about how to draw that again too. So let's have more, but we need to put them all in the right place. So in the case of more, you want as many of the large substituents in the equatorial position as possible. But again, we need to convert from our little drawing here to our chair and boat configuration. So the first thing we do is draw 2 parallel lines, 2 parallel lines, 2 parallel lines. And we're going to put, this is our 1 carbon. And so we have a methyl group, CH3 going up and the hydrogen below it. And over here we have a hydrogen on top. So the hydrogen's on top with the methyl below it. And on this one we have the CH3 on top with the methyl group below it. Did you see how I converted that? I do believe there's a group me for the class, and I think somebody put it in the conversation in Canvas. Okay, so did we see how to convert this drawing into this drawing, making sure that we keep the group that's on the top, and the group that's on the bottom by assigning one, then the other, one, then the other, and one, then the other. Okay, great. Okay, so now that we've done that, let's go ahead and take a look at that. First of all 3 of those methyl groups are in an axial position. Okay, so that means when we flipped it the other way, all 3 of them are going to be in a equatorial position, because all axials become equatorials when we flip it. And that means we'd have 3 groups in the axial position on this drawing and 3 groups in the equatorial position on that drawing. So which is going to be the more stable? The all equatorial or the all axial?
Equatorial?
All equatorial, and it's going to give you the most stable system there. And it can flip back and forth, but of course it's going to stay where the 3 methyl groups are in the equatorial position most of the time. Okay, so we've done 1 group on a cyclohexane, we've done 2 groups on a cyclohexane, but we're cis and trans, we've done 3 groups on a cyclohexane, and that is the depth I want to get you to understand about cyclohexanes. Okay, so key phrase here is, when you're looking at this, and our cyclohexane is our most stable ring here, by flipping it back and forth, you try to find the most stable conformation by putting the largest groups in the equatorial position. Okay? Questions on alkane rotation around sigma bonds and or cyclohexanes and flipping them back and forth? Okay, so what I'm going to do is I'm going to stop sharing this right here. And I am going to do an extra lecture on resonant structures. Okay, here we go. Yeah, I'm going to do an extra thing on resonant structures. Here we go. I'm going to share my screen. All the slides are on Canvas under the Slides tab, under Resources. including this extra bonus lecture. It's on there as well. Okay, there we go. Can we see that? This is kind of going back to module 1, but it's about the resonant structures and easy ways to patterns to recognize and things to understand about resonant structures. This is just diving in a little deeper than I did already, but it can be, when I have time, I like to add this lecture because it gives some extra depth to the thing. So the first thing we want to do is in chapter 1, we wanted to understand the electronic structures. But when we come to resonant structures, that gets a little confusing. And I talk about how resonant structures, when you spread charge out over more areas, things become more acidic. And I talked about resonant structures when we were talking about acidity. So I wanted to revisit that and show you some really cool ways to just move electrons around in your resonant structures and get them to be where you want. Okay, so of course, a resonant structure is just equivalent Lewis dot structures that are different in some way, but all the other things are the same. It has all the same number of bonds, all the same number of electrons, all the same number of attachments. But the only difference is where you drew the electrons existing, either as a double bond or as a lone pair. Okay, so in the case of this nitro anion right here, we have, so in this configuration, we have an oxygen with a double bond. We have a formal charge of +1 on nitrogen, a formal charge of -1 on oxygen, on both oxygen, giving the net charge on that molecule a -1. Okay. Now remember, when we were using nitro group as an electron withdrawing group, we also said it had a formal +1 charge, and that's why it was such a strong electron withdrawing group. Now, why can't we just take these electrons, kick them in here, and kick these electrons out here to draw this structure? There is no reason we can't. Therefore, these are equivalent structures. But it's saying that you can now have the charge is no longer on this oxygen. It's now been transferred to the oxygen without charge. And again, we can do that because we have 3 equivalent oxygens. So we can move that 0 charge oxygen around their system. And so what's going to happen is it's probably going to be sharing all that negative charge around all of those atoms. Okay. So if we do some math here and we look at how much of the charge is actually residing on each of these atoms, in this conformation, we have a -1, we have a 0, and we have a -1. So over those 3 structures, we have 2 minus charges over the possibility of 3 structures. So if we have 2 minus charges and divide that by 3 atoms, we have 2/3 of a negative charge on that one atom. So it's not 100% negative, it's only 2/3 negative. And that's true for the other 2 equivalent oxygens. So it only has -2/3 charge on each of those. But notice that positive charge stays on that nitrogen. It doesn't get shifted anywhere. Okay. So by looking at these resonance hybrid, by looking at these resonance structures and saying, okay, well, that means that there's, part of a double bond here, part of a double bond here, and part of a double bond here, what that gives rise to is this structure here is what we call our resonance hybrid structure. See how we have the dashed lines right here? These dashed lines indicate that we have a partial double bond, but it's not always on that thing. So it kind of moves around. That double bond moves around and is in each of those positions 1/3 of the time. Okay. So we go from our 3 equivalent resonance structures to our resonant hybrid structure. So how does it only happen in those kind of systems? No, it also happens in carbon systems. And we're going to see reactivity of these alkenes take a role in where the reactions happen because of resonance structures. Okay. So remember, resonance structures have all the same connections and all the same atoms that only moves electrons around. So let's look at a carbocation next to an alkene. Okay. So we have extra, we have these 2 electrons in the double bond here, and we have a negative charge over here. So isn't not equivalent to put the 2 electrons here and then end up with the positive charge on this side? So this is one resonance contributor. This is the other resonance contributor. So all we've done is flip that double bond. Now, if we wanted to draw that as a stick drawing, we just put it where the charge moves to the other carbon, and the double bond flips between the two other carbons. Okay, so that means that positive charge spends part of its time on one end of the molecule and part of its time on the other end of the molecule. So our resonance hybrid structure for that would be this right here. So we have a partially positive terminal carbon, a partially positive terminal carbon, and we have these two partial double bonds. 50% of its time it's one place, 50% of its time it's the other place. Okay. So if it's flipping back and forth so quickly, how is it able to do this? Okay, now that's where understanding that our on one side of here, we have let's start with the cation here. And so this is where our double bond is, and we have our cation here. Our cation is an sp2 hybridized carbon with an empty p orbital. So there's one electron here, there's one electron here, and there's 0 electrons here. Actually, let me use numbers. So this p has 1 electron, this p has 1 electron, and that carbocation has 0 electrons. So all that has to happen is they all have p's, they're all aligned. Just move the electron from here to here, and now our positive charge is on this side. Okay, we didn't change orbitals, we didn't change locations, we didn't change bonds. All we did was move where the electron was. And that's the benefit of these resonance structures. We get to see the changes. Hybridization didn't change, bond order didn't change, nothing. All we did was move that electron. And if we move that electron back over here, our positive charge goes back to there. And so it's going to flip back and forth very easily because those orbitals are overlapped just like that. Questions on that? Now, this type of resonance structure with this positive charge on it is going to be valuable because we'll be able to see things that react differently than we think they're going to do, but they react that way because of these resonance structures. Okay, so let's go ahead and do 4 rules for drawing resonance structures. Okay, so the first thing is the positions of the molecular ion does not change amongst the resonance form, meaning that we are not going to break any bonds, we are not going to move any atoms. They have to have the exact same connectivity to everything. However, double bonds and charges can move because those are just electrons. Our second rule is only electrons can participate. Now that can be a lone pair, that can be a double bond, that can be a radical, that can be anything that's just electrons can move around. Okay, and remember, charge is the lack or excess of electrons, so the charge can move around as well. Okay, so only the electrons move, no atoms, only electrons. Okay, so then the 2 other rules is sigma bonds do not participate in resonance ever. You cannot break a bond. Okay, and the overall charge of a resonance structure should never change. If you have a cation in one resonance structure, you have to have a cation in the other one. If you have a radical in one, you have to have a radical in the other. If you have an anion in one, you have to have an anion in the other. Okay. So with those 4 basic rules, let's look for some patterns. Okay. So because of our rule about the octet rule, we can also never have 5 bonds to carbon. Okay. So that means we cannot draw a resonance structure where the lone pair of the oxygen comes down here and gives us charge separation. It breaks 2 rules. It has more than 4 bonds to carbon, and it has a different charge than the starting material. So that means this cannot be a resonance structure. The charge changed, and we have too many bonds to carbon. Okay. All right. So likewise, when we have a system where we have a nitrogen there instead, we have, again, a change. We have the same charge we have here, but now we have too many electrons. We've overfilled our octet. In this place, we've overfilled our octet with 10 electrons. In this place, we've overfilled our octet with 10 electrons. So we can't break the standard rules of Lewis dot structure either. Okay. So then when we have our ions can move a couple different ways. You can move 1 electron, and when you move 1 electron, it has a single barbed arrow. So 1 electron is a single barbed arrow, signifying you've moved 1 electron. If you're moving 2 electrons in a lone pair, you get 2 barbs on there for each, one for each electron. Now, one of the things we've been mostly doing is when we move electrons around, we typically move them in pairs. However, in chapter 8, we're going to talk about, chapter 10, we're going to talk about radicals. That's where this one's going to come in. So that being said, we can move our charge by moving some electrons to move where the charge is. So in this case here, like the one we showed with the carbocation of the propylene right here, we saw that we just moved these 2 electrons over here, and that gives our positive charge, or our empty p orbital, on the other atom. And because they're equivalent, they have the same charge, they have the same number of atoms, they haven't broken anything, they just moved where the charge is. That's a valid resonance structure. Okay. Now, let's look at the opposite of that. Instead of having a positive charge on that carbon, let's put a negative charge on that carbon. What does that mean? Well, that means we still have that sp2 hybridized carbon, but we have 2 electrons in that p orbital. Now that p orbital is next to those 2 p orbitals of the pi bond, and that can also participate in that resonance structure. So if we took those 2 electrons and put it in between those so it creates a double bond, we have to take that, both of these electrons that were in this bond, and put them in this orbital, giving us our anion on this charge now and our double bond on this side. So see how we have the same number, same charge on both sides, and same number of electrons and bonds. We just move 2 electrons around to create the new equivalent resonance structure. Okay, let's see. All right. Okay, so that works for radicals as well. If we just move one, if we have one radical, if we have an unpaired electron in a system, both resonance structures have to have an unpaired electron. And so in that case, we'll have 1 electron go and form the pi bond, 1 electron from the pi bond coming over here using single barbs, and that leaves the remaining electron on the other atom. Okay, so we're going to see this kind of pattern, especially when we get to the chapter 10. But see how we're moving single electrons with that single barbed arrow. Okay, so can you determine whether one resonance structure is better than another resonance structure, meaning it's going to spend more of its time in that? And well, yes, we have some rules about that. We're going to evaluate the relative importance of which resonance structure is going to be there more often. This comes into play especially when we're looking at mechanisms of something, where we want to say, okay, these 3 resonance structures are possible, but our major product is this. And we can usually define the most stable or most probable resonance structure based on these rules. And we'll show you that selectivity of the reaction. Okay. So the first rule is resonance structures in which each atom has an octet generally make up the greatest contribution of overall electronic structure. So you imagine you want to have octet on as many of the atoms as possible, except for, of course, hydrogen. So if you have somewhere they have charge but not an octet, and you have one where you have 2 charges but not an octet, you want to look at the one that you can actually have 2 charges and an octet, which will be more stable than not. Okay. So then the second rule is resonance structures in which the formal charges are minimized is more important than those with higher formal charge, meaning that if you can draw a resonance structure with 0 charge, or with just one, like a positive or a negative charge, as opposed to, oh, well, I can flip these electrons around and I get a positive here and a negative here, or I get 2 negatives and a positive. The ones with the more charges in it are less of the less importance, and those are going to be less likely to be contributors to the reaction. Okay. If formal charges are present, you want your negative charges on electronegative atoms, like oxygen, nitrogen. If you have a positive charge, you want it on the less electronegative atoms, like carbon and boron. Okay. it makes sense because the more electronegative atoms are more likely to have that want the electron to make it negative. And so that's where the negative charge is going to lie. So if you're drawing a resonance structure and you have a positive charge on oxygen and a negative charge on carbon, that's probably not going to happen very often, okay, because oxygen is much more electronegative. Okay. Now, rule 4 is that the resonance structures in which atoms have like charges are connected are extremely unlikely. What that means is that if you have a carbon with a positive charge next to a nitrogen with a positive charge, you have 2 positive charges. They are repelling each other. You're never going to have those resonance structures where you have the same charge right next to each other. So whenever you accidentally draw one like that and say, oh, wow, they both have a positive charge or both have a negative charge, that's not going to be a important resonance structure. Okay, so let's use these rules and use those rules to evaluate all of these resonance structures for this amide that we have and figure out which one is the most important or the most valid right here. So first thing we do is we draw a valid Lewis dot structure. So we have 2 electrons around hydrogen, 2 electrons on hydrogen, 2 electrons on hydrogen. We have 8 electrons around nitrogen, 8 electrons around carbon, and 8 electrons around oxygen. So we have a valid Lewis dot structure right here. Now let's go ahead and make sure we've put our lone pairs in correctly right here. And so they're in the correct location as well. Now let's start playing around. Okay, so the first thing we want to do is, okay, well, let's go ahead and in our first resonance structure, we're going to take these electrons and move them to the more electronegative atom. Okay, when it does that, we now don't have 8 electrons around carbon, and we have the positive charge and a negative charge. Okay, so between those two, which is the more probable resonance structure between the one with the charges and the one without the charges?
One without.
The one without the charges. However, this is a valid charge because the positive charge is on the the less electronegative atom. The negative charge is on the more electronegative atom. So we're still not breaking a rule. And we have opposite charges. So this is still valid, but this is more stable because it meets that having as many atoms have octet as possible. Now, if we start playing around and say, well, okay, so we did that, but there's these electrons here that can move here to stabilize that positive charge. What's that look like? Well, when we do that, we now have a positive charge on an electronegative atom and a negative charge on an electronegative atom. So that's even going to be less stable than this one because the positive charge on carbon was the less electronegative atom. So this is even going to be less stable than that. And then if we move over here, we're going to, if we take these electrons and put them on the carbon, now, wait, hold it, where'd they go? No, we've moved the electrons from the oxygen down to the carbon. They actually flipped all the way there, giving us our electrons back here. Now we have a negative charge on the least electronegative atom. We have a positive charge on the most electronegative atom. And we have 2 atoms that don't meet the 8 electron rule. So that's even less. And so that's not even a valid Lewis dot structure because we have, the charges on the wrong atoms. So that's not even a valid structure. So just comparing these, the number 1 structure meets all of the rules for the most stable. And so even though we might see these briefly in solution, particularly this one we might see a little bit, and this one we'll probably never see. But because we could probably see this in solution, that wouldn't be here, but it's going to be this 99% of the time, okay, because it has the most stable resonance structure. Although these other 2 are valid resonance structures. Okay. So let's see a few patterns. There's going to be some real common patterns we're going to see. Okay, so one of the first things we're going to see is that a lone pair of electrons that is next to some other double bond is going to be easier, it's going to be easy to move around. So let's see what I mean about that. Okay. So if we have a lone pair of electrons near another double bond, that means that lone pair can come in here and create a new double bond, and that other pair of electrons can go and end up on a more electronegative atom. Okay. So we just actually, interestingly enough, when we do that, I mean, we still have our double bond, we still have our connections, but which of these two is probably more stable based on what we know about wanting the charge on the more electronegative atom? Is the charge going to be on the oxygen or the nitrogen?
Oxygen.
The oxygen, because it's more electronegative. So this is actually going to be a more favored resonance contributor. Okay, but we're also recognizing that pattern of a lone pair next to a double bond gives us this really easy pattern to flip back and forth. Okay, so let's do that again over here. Over here, we have the lone pair on the oxygen right here that can flip down and give us our charge on that carbon. Okay, now in this case, which is more stable, the charge on the carbon or the charge on the oxygen? Which one's more electronegative?
Oxygen.
The oxygen, right. So this is going to be the major contributor here because of that. But again, the pattern is lone pair of electrons and a set of double and a double bond. Okay, so it can happen again here. So we see it a lot in carbonyl compounds and alkenes, where this can kick up and over. Now notice we have a positive charge here and a negative charge here. So we go from an uncharged species to a two charged species. So this is going to be the major contributor, but the fact is those electrons can do that. And in this case here, we're going from a negative charge on a carbon next to this double bond and kicking it up so the negative charge is on the nitrogen, which makes this the most stable resonance contributor in that pair. But again, it's the same pattern. And they're called allylic lone pairs. Allylic means that they're on an atom adjacent to a double bonded system. So it can be a carbon-oxygen double bond or a carbon-carbon double bond or a carbon-nitrogen double bond. Okay, it's just a lone pair on the next atom over from a double bond. And so it can flip back and forth and move those electrons around. Okay. Second pattern I want to talk about is the same thing, but with a positive charge. Okay, instead of having a lone pair do the work right here, we have the positive charge do the work. Okay, so if we just have a positive charge and a single alkene right here, in this case, the propylene right here, that cation can spend half its time on one side and half its time on the other. Okay, and if you have another connection, we can actually move these electrons here and create our charged species in the middle, but there's no reason it can't do it again, have these electrons kick in and have the charge at the other end. So in that case of having this butadiene, I'm sorry, this is pentadiene, that positive charge can be at the end, the middle, or at the other end, just by resonance. And all of them are going to be contributors here. Now, oh, okay, yeah, we'll do it. So the other cool thing here is these are ways of looking, these are special names for the types of carbons and or hydrogens we have. They're the different positions available to us when we have double bonds. So if it's part of the alkene itself, that's the vinyl group, and so we call those vinylic. And so that's the vinylic carbon or the vinylic hydrogen, or if we had a chlorine there, it would be the vinylic chloride. Okay. Now, the one next to it on either side, if it's bond on either side, is the one bond over is called the allylic. And that allylic is really a great place to shift electrons to and from because they're readily available next to that double bond. Okay, so that's pattern two. Pattern one was allylic with a lone pair. This is allylic with a positive charge. Okay. Now, the next one is a lone pair adjacent to a positive charge. Okay, so what we have in this case here is we have a valid resonance structure. We have our positive charge on carbon, the less electronegative, the negative charge on oxygen. But we can eliminate that charge, those opposite charges, by doing this. And so really, in our structure of our carbonyl compound here, we actually have part of its resonance structures here, making this the partially positive side, this the partially negative side. And so that's going to give us our reactivity. If we have a positive charge on a carbon and we can move electrons in, we can then create this system now. Now, again, the positive charge on carbon is more stable, so it's the major resonance contributor. But you have that lone pair to balance that positive charge. In this case, we actually eliminated charges. Here, we just move the charge to a different atom. Okay, the fourth one is the pi bond between two things of a different electronegativity. Okay, whenever you have a pi bond between a carbon and carbon, you aren't going to have one carbon be positive and one carbon be negative. There's not a really good driving force for that. However, if there's a difference in electronegativity, then yes, part of your time, the more electronegative atom can have the negative charge, and the less electronegative atom can have that positive charge part of the time. And that works for nitrogen, oxygen, and carbon. Here we have the nitrogen being more electronegative, can have the negative charge on it and the positive charge on carbon. And those are perfectly valid resonance structures, but the ones without charge are more stable. Okay, the next thing we have is rings. If you have alternating single and double bonds in a ring, there's nothing that's going to keep them from moving around. Okay, so all we have to do is flip. If you flip one lone pair, you flip one lone pair, you have to flip the next lone pair and the next lone pair, and you end up with equivalent structures. Okay. The sixth pattern is where you can move that charge around the ring. We did this when we were looking at the base strength of amines, where we saw that we could have the charge and also on the acid strength of the phenoxide ion, because we could spread this negative charge over a total of 4 atoms, it was more acidic than an alcohol where it could not spread that charge over anywhere. So that phenol, that oxygen on a benzene ring, was more acidic because of that. And so you can see we can spend part of our time with the charge here, the charge here, the charge here, but more of the time with the charge here. And that's what gives it its acidity, to being able to spread that around the ring. Notice we start with the charge outside the ring and then move it inside the ring. And then it'll all eventually get outside the ring. Okay, our last thing I want to talk about is localized versus delocalized electrons. And the idea here is that if you have sp or sp2 hybridized atoms, you have that p orbital, right? And if those p orbitals line up with each other, they can share electrons with those p orbitals. Okay. However, when you think about that lone pair, the fact that the p orbitals are what's sharing this positive charge back and forth here, notice that the oxygen here is sp3 hybridized and the carbon at this end are sp3 hybridized, meaning they don't have available p orbitals. Okay, so it's more likely that it's going to have to move into back and forth right here and be kind of focused, just flipping back and forth. It's going to be much more stable for the compound than for it to have to change the hybridization of that oxygen over here and get to this position. So I think the resonance contributors for here and here are going to be higher because you don't have to change hybridization to get to this structure here. So what we call is that a localized is when we can want the electrons to stay in one place, and delocalized is when we can put them over a variety of bonds. So the lone pair and the charge here is what we would call a delocalized system, and the ones at the end here are localized. They don't move at all. Okay, so let's look at this in a ring. It's more common to have delocalized in a ring. But so in this case here, we have our lone pair on our pyridine here, and we have double bond. However, if we tried to put these sp2 hybridized electrons into the ring, we'd end up with a very weird structure. Notice we have 4 bond, we have these really strange system here, and we have this negative charge on carbon and the positive charge on oxygen. It's not a valid resonance structure because we have the electronegative atom having a positive charge and the electropositive atom having a negative charge. Therefore, these electrons are localized on that nitrogen. However, these electrons in the ring can flip around, and so they are delocalized in the system. Okay. All right. So that was just some extra little tidbit I wanted to get to you on the writing up some Lewis-Dot structures and looking at various patterns to look for when you're moving stuff around. As we go into reaction mechanisms, we're going to do a lot of electron pushing and realizing there's certain patterns here. It's not just, you don't have to recreate the wheel every time. You should start looking for these patterns. Okay, so I'm going to stop share. And that's all I have for you today. When we come back on Tuesday, we're going to do a review for our exam. Okay? So sorry I didn't fill up the time here, but you get to go have an extra cup of coffee.
Thank you.
Thank you.
Thank you.
If you want to stay behind, go ahead. I'm going to stop recording.
Have a good day.
Thank you. You too. Hardly ever finish early. That's weird. All right, if nobody has any questions, I'm going to go ahead and close out and start the thing processing.
Hey, Dr. Irvin, I have one quick question.
Okay.
So I noticed that next week we have our test, and it's on the 17th, I believe.
Correct. No, it's on the 18th.
The 18th. Okay,
Yeah.
sorry. On the syllabus, it says the 17th, and I was confused.
Right. Yeah. So the on the syllabus is wrong, and it looks like the exam schedule here is wrong. So I'm going to go ahead and go in and edit that as soon as we get off so I can make sure. But yeah, we don't meet on the 17th. It's during class time on the 18th. In fact, I'm going to go change it right now on the syllabus. I just changed it on the exam schedule right there.
Okay.
And it's actually on the syllabus. Oh yeah, that is wrong on the syllabus. I'm going to change it on the syllabus right now.
Okay, cool. Well, thank you so much for everything, Doctor, as always. You have a great weekend, and stay safe out there.
You too. Mask up. Let's get back to school next semester.
Yes, sir.
All right. Bye.
Bye.